Good morning. I hope everyone is doing well. So what I thought I would do today is I debated whether to go on to Ion Exchange or look back at what we talked about in terms of the water and wastewater tour that we did a exercise on Monday. I have more information. I have some more photos that I've added. And in fact, I spoke with the utility director of the Genoa plant, Greg Tatara. Greg is a MSU grad. He obtained his PhD back a number of years ago. And I asked him for what initially was one photograph, sent me a bunch of photographs, and from that ended up a video tour of the plan. So we'll look at that and we'll just kind of go through the plan. I did contact the plant supervisor of the East Lansing plant to ask about the scuba divers. They were not affiliated with the plant. The only thing I have come up with as an alternative is there is a scuba diving course through kinesiology at MSU. And I know this because my son took the course a number of years ago, and they, in a normal year, would go down to a quarry in Ohio, and that's where they do their certification for scuba diving in turbid water. Well, Red Cedar's pretty turbid, so maybe that's what it was. I don't know, but it's not affiliated with the plant. So any questions before we start? So what I thought we'd do is we'll go through and we'll look at these two plants. And as I mentioned Monday, basically these are two plants. So we can think of this as being divided right down the middle here. Okay, so this is plant 1 and this is plant 2. Plant 1, as I mentioned on Monday, is the older plant, and then 2 was built, I think about 10 or 15 years later. So this is again, the same aerial drawing where I've labeled the buildings. So the wastewater comes in here. It initially now goes through the grit chamber. So this is the grit chamber here. It goes from the grit chamber through a splitter here, and it can go either to primary 1 or primary 2. The equalization basin that is under the parking lot all of the flow used to go into the equalization basin. Now it's really used for wet storage. So at high flow, when they need to divert some of the water into that equalization basin, they can do so. It's a 5 million gallon basin. The blowers here, so this building here is the blower building. Initially, when they built the equalization basin, the thought was that they would aerate the equalization basin in order to keep the sewage from going septic, keep it aerated, keep it well mixed. They, as I mentioned, had problems with the diffusers and the piping corroding, so they stopped operation of the blower quite a few years ago. So then the wastewater goes from the primary tanks into the aeration basins, and then from the aeration basins it goes into the secondary clarifiers. Some of the sludge from the secondary clarifiers gets recycled back. So that's the return activated sludge. Some of it is wasted, and that would be the waste activated sludge. And the sludge processing building here has a flotation unit. They do sludge handling, and then the sludge goes to this building here, which has a hopper, and then the sludge is then sent to the Granger biolandfill. The water from the secondary clarifiers are then recombined here, and they go to the tertiary filters. It goes to then UV disinfection, and then to the outfall here and to the Red Cedar River. Any questions about the flow of water?
Yeah, I think we went over this, but how do they determine like what portion they're going to recycle of the activated sludge versus what they're going to waste?
So they monitor the BOD, they monitor the MLVSS and the MLSS in the sludge tank. And based on that and the amount of flow into the plant, they then can determine how much they waste and how much they recycle. So you want to maintain a consistent level of microorganisms. In the basin, you also want to maintain a consistent food to microorganism ratio in the tank. So based on that, they can then determine how much sludge to waste. They also have chemical storage here. So they add ferric chloride. They have a very stringent phosphate limit, and they add ferric chloride. Doesn't look like in this photograph that they were using the last two of the tanks here, but what they would do is they add ferric chloride at this point here, right before the clarifier. So they use the clarifier as an additional reactor. So this precipitates the phosphorus as ferric phosphate, and that ferric phosphate is then collected in the sludge. Because it's in the sludge, they are actually recycling some of that phosphate back with the return activated sludge. As I mentioned here, these are the old ash cooling lagoons. So it used to be that they had an incinerator. They incinerated the biosolids, and then the ash went into these cooling ponds here, and they actually used the ash to fill much of this area along the railroad tracks. Any questions? So I have a few pictures. A lot of them are old. This is actually the old schematic of the plant. Does show the equalization basin. With the new upgrades that they're doing now, you can see this still has dechlorination, and it actually shows the line here up to Kalamazoo. So that no longer exists. They're no longer pumping water up to Kalamazoo Street where there was the outfall. So this no longer exists. They no longer need to dechlorinate because they now have UV, and they're still continuing to do construction. They're adding a digester. They're doing upgrades on the secondary clarifiers, and I believe some upgrades on the aeration system. So they'll be changing the sludge processing, the way that they're actually processing sludge. So it'd be interesting to see how that changes over the next year or so. And hopefully, if all goes well, maybe next year we'll actually be able to go back to the site, and maybe we'll produce a video that we can actually show you. You can take a look at, see how it's changed. This is just the schematic. So you can see here, I haven't talked a lot about sludge processing, but you can see here's the waste activated sludge. It goes through dissolved air flotation, then has sludge storage. We'll talk about belt filter presses. So what you're doing is you're trying to dewater. The water from here goes back to the headworks, as does the water from the sludge dewatering. So basically what belt filter presses basically presses out the water to produce a sludge that's about, I think it's about 20% solids, and that is sent to the Granger landfill. And this actually does have, I changed it. The schematic, if you look online, still shows the chlorination, dechlorination, but I changed that and put in the UV disinfection, which is what they have now. So this is just a few photos from the plant. I actually pulled these from some of the slides that I showed you before. You can see the grinder. So the grinder is at the headworks of the plant before the grit chamber. And as I mentioned, these are the wipes that are supposed to be flushable, that are not flushable, that cause serious problems and clogging in the treatment systems, in the pumps, in the pump stations. And operators absolutely hate flushable wipes. They're not flushable. This is the primary settling. You can see the weirs here. The water flows over the weirs and then to the secondary, to the aeration tank. And you can see the scum collector here. So that is scum collecting floating material. You can see the floating material in this image here, collects that into the scum trough, and that typically is landfill. So here's are the aeration tanks. These are the oxygen lines. So oxygen is added along the length of the serpentine tank. You want to keep the sludge, your microorganisms, the wastewater, you want it well mixed, you want it well oxygenated. So you can see this mixing, and it flows in a serpentine pattern. It's held in these tanks, typically on the order of about, I'm going to say about 8 hours, ranges, but typically around there. The mean cell residence time, on the other hand, is on the order of days, as we discussed. These are the secondary clarifiers. The wastewater comes in from the middle, so it comes in here, flows out, and then there are weirs along the outside of the basin. You see, it's much clearer than in the primary. The primary tank, it's kind of, the wastewater is kind of a grayish color. It's much clearer here. So it goes from this tank, then into the tertiary filters, and now through UV disinfection. So this is the Howell plant. I've added the or labeled the various units, and we talked about this in terms of storage. So I didn't label it here. This is the aeration basins here, and similar operation to the East Lansing plant. Difference is the sludge from this plant is land applied. So the sludge from the East Lansing plant goes to the Granger biolandfill. The biolandfill, they actually collect the methane from the biolandfill and then use it for energy generation. Here, the sludge is land applied. And this is just the schematic showing this. I'm not going to go into any detail. We talked a little bit about this on Monday. And this is just some images of the plant. So what you have are raw wastewater, these pumps. These are screw pumps. They're very, very commonly used with wastewater. This is the influence screen system. The wet weather storage basins look like they're actually refurbished aeration tanks, which may very well be the case. You will find in most wastewater treatment plants, you'll see that there are unit ops that are no longer needed, or they need a larger basin. And as a result, that basin is then refurbished. When we do a virtual tour of the Williamston plant, you'll see that the tanks used for disinfection were actually designed, I believe they were designed as aeration tanks, but I forget. There may have been a clarifier. But we'll find out that when we have our guest speaker. But you'll see that typically tanks are not removed. They're left there and then they're repurposed for some other use. And as you watch the video from the Genoa plant, Greg talks about that in terms of how various different buildings or unit ops are refurbished. This is their aeration tank. Again, the same thing. It looks like in this tank that they're not adding oxygen along the entire length. You don't have to add oxygen along the entire length, although doing so maintains a more constant oxygen level. And then you see here, you see the weir, and the weir is only on one side of the launder, and then the water flows over the weir into this channel, and then from that channel, it would then flow, in this case, to the tertiary filters. So here's a picture of the final settling tank. Here is the UV system. Notice it's open, and Gary will talk more about that on Tuesday. And they have pressure filters. So it's different than the East Lansing plant. The East Lansing plant has gravity filters. They look pretty much identical to what we've seen in the water treatment plants. But here it's a smaller system and they use pressure filters. So this is the Genoa Osceola plant. What I'm going to do now is I'm going to switch to the video. As I mentioned, I asked Greg Titera for one photo, and he and I kind of get talking, and what resulted from that was the video.
Hello, my name is Greg Titera, and I am the Utility Director for the Genoa Osceola Sewer and Water Authority. It is my pleasure to share with you today the Genoa Osceola Water Reclamation Facility. At this facility is our responsibility and our goal to protect the environment by creating clean, quality wastewater treatment plant effluent. The Genoa Osceola Wastewater Treatment Plant is located in Livingston County, Michigan, between the cities of Howell and Brighton, and serving Genoa and Osceola townships. Our plant serves a population of 15,000 residents and businesses in the local area. Our average daily flow currently is about 1.35 million gallons per day. We maintain 92 miles of gravity sewer and force main. We also maintain 40 pumping stations to bring the wastewater to our facility. We do all this with a staff of 9 full-time employees, and our current operating budget is just a little over $2.3 million annually. This is an aerial photograph of the Genoa Osceola Wastewater Treatment Plant in March of 2018. This photo was taken prior to us beginning a plant expansion that we started in June of 2018. The expansion was necessary due to development pressure increasing the flows that our facility was receiving. And our current facility was nearly 20 years old and in need of some upgrades. By creating both an expansion would allow us to meet the future demands as well as rehabilitate our existing wastewater treatment plant processes and bring them into the current technology of today. This picture was taken in August of 2018, shortly after groundbreaking. You can see here we have the 2 holes dug for the 2 final effluent clarifiers, and this was the first stage of construction for the project. This next picture was taken in November 2018. In this photograph, you can see the 2 final effluent clarifiers being poured, as well as the excavation for the oxidation ditch that would be located in this part of the facility. We also began uncovering and reutilizing an old existing sludge storage tank that was going to become our flow split structure to split our flows evenly between the 2 oxidation ditch processes. In April of 2019, you can really see the plant coming into shape. In this particular photo, we were actually water testing the 1 final effluent clarifier and had the second one poured. You can also see the foundation for the return activated sludge building, as well as the total outline for the floor and walls of the oxidation ditch. In addition, you can see some additional excavation for the flow split structure that would split the flows between the 2 plants. In June of 2019, really you don't see too much of a difference, except you can see additional walls being formed for the oxidation ditch, as well as the walls being built for the RAS building, and also some further removal showing the full sludge storage tank that we repurposed for being a flow split structure. And this other sludge storage tank was going to be repurposed as an equalization tank to contain a significant set volume of water through our plant process. As everything at this facility is pumped here, it's important to have continuous flows equally going to the oxidation ditch rather than surges from the pump stations operating periodically. In September of 2019, you can see the skimmer arms and scraper arms going into the final effluent clarifiers. The RAS building is fully constructed. All of the walls are fully poured and installed, and the catwalk is going over the oxidation ditch. You can also see that they began waterproofing the roof of the flow split structure at this time as well. In March of 2020, you can see that our new plant is in operation. You can see the activated sludge and the rotation in the oxidation ditch, water in both the final effluent clarifiers. You can see the new parking lot and asphalt poured, and you can see that we've begun site restoration of the grounds around the facility. And finally, our final completion now with grass fully restored and everything in operation. You can see in this particular photo that the oxidation ditch is fully operational, as is the final effluent clarifiers. And in the old plant, you can see we've emptied out the final effluent clarifiers. And these trucks here are actually painting of the old steel and stuff from the old plant as we begin the rehabilitation process of the old oxidation ditch at the plant. So let's go through the process of the Jean Osio wastewater treatment plant. Historically, the very first phase of this plant was these 3 sequencing batch reactors that were constructed in 1988. This was originally a groundwater discharge facility and used SBRs in order to get full nitrification and denitrification for discharge to groundwater. In 1991, another SBR tank was added on due to growth in the area requiring additional capacity. In 2000, the headworks building, additional sludge storage, and this particular plant were constructed to serve higher demands in the area. Also, as a result of water softener usage in the area, we had a significant sodium and chloride plume in the groundwater created from discharge of wastewater to the local grounds and then getting into the aquifer that was used for drinking water. As a result, we also added a building here to provide tertiary treatment and pumps to pump it back uphill and go to the Marion Genoa Drain, which is a tributary of the Shiawassee River. So at this new process, you can see we have a multitude of force mains coming in. There's actually 4 individual force mains that come into the plant. They go into our headworks building where we screen the wastewater for removing all of the large particulate solids. These are our sludge storage tanks that are used to store sludge. Originally, our plant was would apply biosolids to the ground, but in 2015, we built a sludge press building where we press our solids now for landfill disposal. We also have built a large storage barn here in 2012 to keep our Vector truck and loader equipment. And we also built a Vector dumping station right here, which is where the debris that's cleaned out of sewers can be deposited and placed in the dumpsters after it is dried, and the water is actually treated through the plant again. We have an administration building here that houses our lab, our mechanical rooms, our electrical rooms, and office space for the operators and collection system staff. Again, we also have our final effluent filter screening, UV, and a final effluent pump station. The new plant that was added onto, just recently completed here in 2020, has repurposed 2 sludge storage tanks for equalization, flow splitting, a very similar oxidation ditch of equal capacity to the existing one with a capacity of 1.6 million gallons per day, an additional RAS building, 2 final effluent clarifiers, and then from the original design, we were able to reutilize the final effluent filters, UV, and pump station, which still had sufficient capacity to treat the wastewater. What I'd like to do now is to take you through each of these individual processes in a little more detail. This is our fine screen. It's a Huber fine screen. It's a perforated plate screen that uses mechanical cleaning as well as high pressure wash water. The diameter of the openings are 3 millimeters, so it does a very effective job in removing even the finest particulate matter in the wastewater. This is critical for us as our plant uses pump stations, and so by the time the majority of material gets to us, it has been pretty well ground up and homogenized. So by capturing this, it keeps a lot of grit and debris out of our oxidation ditch process and allows it to run cleaner throughout the entire plant. Following screening, we go into our flow split structure. As you can see, this was a repurposed sludge storage tank, so we still have the columns and such in the precast concrete structure. There's 2 pipes, one for each oxidation ditch, coming out of the other old sludge storage tanks, and it's now used for equalization. We have 2 flow meters on here, mag meters, and then by having this elevation increase in pipe, it allows us to maintain surcharge, so the mag meters are effective in measuring flow. And then we also have 2 throttling actuated valves here that work to equilibrate the flow between the 2 oxidation ditches. Following the selector tank, the wastewater influent is mixed with return activated sludge in a selector tank. The selector tank works very effectively to allow us to do biological nutrient removal for phosphorus. By using this selector basin, rarely do we have to add any ferric chloride chemical or alum in order to precipitate phosphorus. We're able to use the natural biology of the organisms in order to remove phosphorus from our waste stream, saving us both chemical costs as well as providing a better quality effluent by not having acidic ferric chloride added to the waste stream. This is a closer view of our oxidation ditch rotors and brushes and discs. By using this technology of oxidation ditch, it's a very efficient means electrically in order to get good mixing and aeration of your waste stream. It works much better than traditional blower-based diffusers and coarse bubble diffusers in wastewater. This is a close-up view of the oxidation ditch brushes or rotors. And you can see from this they have a shape of a diagonal triangle that works to trap air and also move the water. And then there's also dimples in here that actually create air bubbles that get transposed in the water as these go around. So with all these discs located on one shaft, one single motor can provide a lot of horsepower for mixing as well as getting good oxygen transfer into the activated sludge process. And this is just another close-up of this showing how violent and how good the aeration is coming out of the backside of an oxidation ditch rotor shaft with brushes. Following the oxidation ditch treatment, we go into our 2 final effluent clarifiers. Both these clarifiers have scum arms or scraper arms on the top that will go into a scum baffle. This water is then brought back to the headworks of the plants for treatment, and this removes any of the grease and floating material still in the wastewater. At the bottom of the clarifier, the pumps pull this off and periodically waste some activated sludge for us to maintain our biological population based on the time of the year and nutrient strength, as well as continually return and mixing with the raw wastewater to help in a biological nutrient removal process. Following the final effluent clarifiers, we then go to our final effluent filters. These are aqua aerobics disc filtration systems. There is pumps located on each of these discs that will pull and vacuum off debris as it accumulates based on the water level rise in this chamber. And you can see here we also provide some additional aeration prior to going into the receiving stream, as we have a dissolved oxygen limit on our water. And this helps scrub any remaining phosphorus particles from the waste stream. Following final effluent filtration, we then go through UV disinfection, and following UV disinfection, we go into a final effluent pump station where we have 3. It's a triplex pump station with an 18-inch diameter force main leaving it to transport the wastewater to a final stage, which is the river outfall, where it goes into the Marion Genoa drain, again, a tributary of the Shiawassee River. And again, this is a cascading outfall, again, to provide aeration for improving the biota in the receiving stream. And you can see how very proud we are of the quality and cleanliness of our water entering the receiving stream. Our residuals are managed through a screw press. This is a Huber screw press, and we take our waste activated sludge and process essentially what we waste every day through this screw press. And you can see here, this is a conveyor that takes the pressed sludge outside and into dumpsters where it's ultimately disposed of in a landfill. And you can see here we put this plexiglass over this so the operators could observe and see, make sure that the conveyors are working properly and transporting the pressed sludge outside. Any plant wouldn't be complete without a computerized SCADA system. This is an overview of our entire plant process. So this is what operators watch continually. And you can essentially go through the entire process of the wastewater plant on this screen. You can see here we start with the screening building. From the screening building, we go to the flow split structure. It tells us the level in the tank, and then tells us how much flow is going into the oxidation ditch. From this, you can see we have the oxidation ditch showing all the rotors turning. We get color indication, green being on, red being off. It then shows our final effluent clarifiers. Our drain pump station is what receives all of our drains from the clarifiers and the filters for retreatment back at the front of the plant. You can also see our waste and RAS pumps running, assuring us that that's continually going on and the flow rates for each of those. We monitor our UV banks, and then we have a final effluent pump station. Again, we monitor the level of that, and this is what's pumping it out to the river. And then we also have our biosolids being monitored, showing the levels in our sludge storage tanks, as well as our sludge pump and polymer pump rates, and also the pressure in our hydropneumatic tank, where we reuse a good portion of our final effluent water in order to do makeup water for the press, as well as use it for cleaning and such processes around the plant. So it's a good source of recycling the water, our final effluent water, for reuse in the plant. This just shows the biological nutrient removal. You can see by manipulating the dissolved oxygen and the oxidation reduction potential, we can aid in the biological nutrient removal. So we try to keep our anaerobic zone in our outer ditch here. This is where we have a lot of facultative treatment of the BOD. As we move in, we get to a high level to provide our nitrifiers the oxygen they need to break down the ammonia to nitrate, so the ammonia is no longer a nutrient in the receiving stream. Also, in addition to monitoring the plant, we also monitor all 40 of our pump stations. This is our largest pump station. It's referred to as pump station number 5, or Geo Main. And you can see for these we monitor the level, which is critical so we don't have any basement flooding. We monitor if our pumps are running and what amps we have. It also tells us the horsepower of those engines. We then also have all of our alarms listed, our generator status, and we have a day tank for our backup diesel generator and fuel transfer pumps as well. So every station has its own independent constructed screen with alarms to provide us with all the communication we need to monitor that pump station, operate that pump station, and respond to an emergency event, as we had just recently this past Sunday with the high winds knocking out power and controls to several of our stations. This is just a little thing we like to show to school kids when we tour, and this just takes you through our process. So you can see this is our effluent. Again, you have the mixed liquor. This is the quality of the effluent leaving, and for demonstration purposes, we always like to show that compared to drinking water to show essentially how clean the drinking water is relative to our effluent. How well does our plant work? This is just some of our September data. So you can see our concentrations here and what our basis of design was based on in terms of designing this plant. So our ammonia is typically about 32. Our total suspended solids are 336. Our BOD is 205. And you can see based on our removal of our effluent, this is how much we take them down to. So our phosphorus leaves at 0.18. Our ammonia leaves at 0.04. Our TSS is 206. And our BOD in the effluent is just a little over 1. So we have anywhere from 99 to 97% removal for phosphorus, 99% removal for TSS, and 99.5% removal of all BOD, indicating that the quality of effluent being delivered to the receiving stream is very good and is very protective of the receiving stream, which is what our goal is.
I want to mention one thing on here. Look at you see the MLSS and the MLVSS. So they're actually operating the plant, the oxidation ditches, at about 4,000 milligrams per liter MLSS. The CRT is the cell residence time. So that's the mean cell residence time. So that's 17 days. So that's quite long. Your food to microorganism ratio is 0.05. They're not providing a lot of food for the microorganisms. So essentially, they're almost starving the microorganisms so that they consume as much of that phosphorus, as much of the nitrogen, as much of the CSC, carbonaceous BOD, as much of that BOD as possible. So and that's why they get such low effluent levels, because they're essentially tricking the organisms, okay, or by having a low food to microorganism ratio, they're encouraging the organisms to consume all of this material or most of this material, giving them very low levels.
This is a picture we like to show as well. So prior to the Clean Water Act, which was initiated in 1972, this is essentially was the impetus in our country to create large-scale wastewater treatment plants to treat. And this is pretty close to home to you. This is the Red Cedar River on the campus of Michigan State back in 1966. And it resulted in the city of Williamston not having waste treatment. This was the quality of the water that people canoed on when you looked at the Farm Lane Bridge to the canoe livery. If you look at that today, you can see it's a much cleaner situation. So wastewater has done a great deal. It's probably been one of the largest public health improvements in our country, in addition to clean drinking water. And that's where environmental engineers and civil engineers have been so critical in improving the health and welfare of our citizens. However, with wastewater, we will have some future challenges facing us. Some of the things that are being looked at now are removing prescription medications from effluent streams, as we're finding that some prescriptions are interfering with larval and fish reproduction as a result of hormones and stuff that are going into the receiving stream. Microplastics, especially microbeads from cosmetics, are becoming a big problem as they're accumulating in the Great Lakes and coming together, creating oxygen-depleted areas for fish. Recalcitrant compounds such as PFAS are unable to be removed by our traditional biological treatment processes. And so we're going to have to work toward the future of finding ways in order to treat these and remove these from the waste stream, as they often become concentrated in the wastewater treatment plant effluent. And lastly, one of the major things we have to do is retaining and attracting skilled personnel in a wastewater treatment field. Operators play a critical role, and as technology develops and computer skills are more and more necessary, as well as communication skills with the public, higher and higher educated individuals are needing to go into the wastewater treatment field. And so retaining and attracting people in this field, which is not necessarily all that glamorous, is one of the key things that we try to do in terms of making it an attractive career, since it is such a large public health benefit to our country. I hope you've enjoyed this tour of our Genoa Osceola Wastewater Treatment Plant. Good luck with the rest of the semester, and I look forward to talking to the Environmental Engineering Group again in January. Thank you very much. Bye-bye.
Almost to the end. So that hopefully gave you some sense of the Genoa plant. These are just some additional photographs that I add in there. I'm not going to talk about the Ann Arbor plant. You did have a question on Monday about water flow through the plant. This is just a typical hydraulic profile through a wastewater treatment plant. And I just wanted to show you this here, that what you can see here is you've got the wastewater comes in this case, at an elevation of 120.5. It goes through screens. It then would go through into a wet well, is pumped up. And notice it's pumped up to an elevation of 130. It then flows into a grid chamber. And notice the elevations. So then it flows by gravity from the grid chamber to the primary sedimentation basin, then by gravity from the primary sedimentation basin to the aeration basin, then by gravity from the aeration basin to the final clarifier, and then most likely by gravity to the outfall. So just to kind of give you a sense of, as much as you possibly can, you want to minimize pumping. Pumping causes problems, and allow the water to flow by gravity through the plant. I'm not going to go through this. It's just a little challenge. If you would like to do this for extra credit, I will put a Dropbox in. I'll just set the due date for about 2 weeks from now. But watch the video. It's a very, very interesting plant. The narration is done by a professor of practice at University of Massachusetts, and he will walk you through the entire plant. It's very interesting in terms of how they operate. Like the oxidation ditch, it's a plant that uses the anoxic, oxic environments to remove phosphorus. So basically by doing that, it's tricking the organisms. It also then achieves nitrification, denitrification. So it's converting nitrate to N2 in order to achieve very stringent nitrogen removal. So like I said, if you like, take a look at that. Watch the video, and you can label the image, and I'll include a Dropbox for extra credit if you'd like to do that. Any questions? Hopefully this was useful. I decided to do this rather than go onto Ion Exchange, just to give you a better sense of the treatment plant operation. Happy to answer any questions. Otherwise, I will see you all, meet with all of you on Friday at our usual time, and we will start Ion Exchange at that point.